Hello everyone, my name is Phan from Queen Mary University of London. Today I'm going to present the work on multitask loss function for audio event detection and localization. So firstly, I would like to give a brief introduction about the problem. Let's say given a multi-channel audio input, for example recorded from a microphone array, and assume that there are several audio events happening in the signal. So the task audio event detection and localization firstly need to determine the identity of the signal of the event of interest that happened in the signal. And at the same time, we're also interested in determining the direction of arrival of the sound sources that generated the event. And in general, the event may happen at the same time and result in event overlap. And therefore, audio event detection and localization is a multitask and multi-label problem. And this problem has been one of the main tasks in the most recent DCASE challenge 2019 and 2020. So there are different approaches people have used to tackle the problem, but in terms of modeling with deep learning, there are two main approaches. The first one, joint modeling approach. Because audio event detection and localization is a multitask problem, and therefore it appears to be natural to tackle it with a multitask model. And this model is expected to deal with event detection and localization at the same time. So such a model usually have one classification branch for event detection and another regression branch for localization. The other approach, separate modeling approach. So in this approach, people try to separate the subtasks of the problem into individual ones and deal with them one by one. So in this case, we have a single task model for event detection specifically, and we have another separate single task model for event localization. So in general, the joint modeling approach is more convenient because we only need to train a single model at once for both tasks rather than multiple models at different time. However, recent studies show that joint modeling approach usually result in worse performance than the separate modeling approach, and we particularly interested in understanding why joint modeling approach underperform the separate modeling approach. And we speculate that there are probably two main factors that make the joint modeling difficult. The first one is the mixed information. So given that event detection usually rely on the magnitude of the signal and the phase information is irrelevant, whereas for localization is the event localization usually rely on the phase information of the signal and the magnitude more or less irrelevant. And when we combine the two information together and present it to the multitask model for training, the mixed input somehow become suboptimal for both event detection and localization tasks. Another problem is the heterogeneous losses, because we usually tackle event detection as a classification with cross-entropy loss, and the localization as a regression with mean square error loss. And when we combine the losses together to train the model, we may end up with some issue. The first issue is one loss may dominate the others because they are different in the magnitude, and therefore weighting is necessary, meaning we need to determine appropriate weights for the losses, but doing that's not an easy task at all. Furthermore, the losses may progress differently during the training course, and making fixing the weight at the beginning may become suboptimal during the training as well. So much research is needed to look further into the issue, but in this paper we propose an alternative approach to perform joint modeling with the homogeneous losses. So the idea is, instead of treating event detection as a classification task, we consider a regression task, and this will allow us to use the same mean square error loss for both event detection and localization. So to showcase that and demonstrate that training a multitask model with homogeneous losses offer more benefit than the heterogeneous losses. We base our investigation in the same network architecture. So this network is actually a CNN. The network receives spectrogram as input. Here I show only one magnitude spectrogram with length t, but actually in practice the input should be multiple magnitude spectrogram combined with features extracted from the phase information, because now in this case we have multi-channel audio input. So the network in the network on the convolutional layer have the same kernel size 3x3, and the first two convolutional layer have the number of kernels is 64. And after that we have a multi-pooling layer to reduce the time dimension by 5 and frequency dimension by 2. The reason is the input we use a resolution of 20 milliseconds, and therefore reducing the time dimension by 5, we end up at a resolution of 100 milliseconds, which is the resolution that used for evaluation in the DCASE challenge. And after that, we have another 4 convolutional layers with the number of kernels increasing from 128 to 256. And each of them is associated with a multi-pooling layer to reduce the frequency dimension by 2. And by doing that, we hope that we are able to learn frequency invariant features for the problem. After that, we have a bidirectional recurrent neural network to iterate over the sequence of convolutional feature vectors and transform them into a sequence of recurrent output features. And to enhance the sequence modeling of the bi-RNN layer, we combine it with a self-attention layer. And the last layer of the network is the output layer. Now at each time step of the model, we have 2 branches of fully connected layer. The first one is for event detection, and another one is for event localization. And the output of the network at each layer, at each time index has 4 columns. The first column is for event activity, and the other 3 columns are for event localization coordinates. And assume that we have C different event category of interest, then each column should have C different elements, one for each event category. And the self-attention layer that I mentioned in the network architecture is actually a scale dot product attention. So in this layer, we use the same Z matrix for all query key and value matrices. The Z matrix is formed by concatenating the recurrent output vectors of the recurrent layer. And as we mentioned that, and I mentioned that we consider event detection as a regression task as well, and therefore therefore we're able to use both mean square error loss for event detection and localization. So in the loss function for network training, we have the first component is for event detection, and the second component is for event localization. And the first sum is sum over the model index, the model time index, and the other sum is sum over the training example. So we conducted experiment on the DCASE 2020 challenge. The data has 14 event category with 714 samples, and the data is provided in 2 different formats, the MIG format and the FOA format. For feature extraction, we use the magnitude log male scale spectrogram with 64 male filters, and for encoding the phase information, we use acoustic intensity vector for the FOA format, and the generalized cross correlation with phase transform for the MIG format. And following the DCASE challenge, we use 4 matrix for evaluation. The first 2 are for detection, and the other 2 are for localization. So to show the influence of the loss functions on the network learning and performance, we conducted experiment firstly with the heterogeneous losses, and we use different weight for mean square error loss and cross entropy loss. So we assign the weight 1000 for mean square error loss and the weight 1 for the cross entropy loss. And and uh, um, the figure here show how the network learn and its performance. So let's focus on the localization error here. We see that the model converges normally, meaning the training error and the test error is reasonable. Whereas in the detection task, we have the model show signs of underfitting because it showed some poor performance on both training and test data. So in another experiment, we repeated the experiment with another set of weight for mean square error loss and cross entropy loss, and we use the same weight one for both losses. And we see that when we reduce the weight for the mean square error loss, we obtain worse performance on the direction of arrival estimation. Uh, Whereas in the detection task, we see just a marginally improvement on the performance both on test and train data, and still the network still shows signs of underfitting. And in another experiment, we replaced the heterogeneous losses with the homogeneous losses that we proposed, and we repeated the experiment. And now we can see that for the direction of arrival estimation loss, the model converges normally, um, and uh, uh, and we see the error on the train and test data are reasonable. And on the detection chart, we see significant improvement on the performance both on train and test data compared to the case when we use the heterogeneous losses. So in terms of the performance on the FA data, we evaluated the models on both development and evaluation data. So let's focus on the test data, on the test result of the development set in these rows, in these four rows. So these two rows correspond to the model with heterogeneous losses with different weighting scheme. And we see that when we use different weighting scheme for the heterogeneous losses, we see different performance on localization and detection between the two models. And when we use the homogeneous losses that we propose, we obtain much better performance compared to the heterogeneous losses cases. And overall, the improvement is around 10% compared to the heterogeneous losses. And compare with the DCASE challenge baseline in here, our proposed system is also significantly better. Better is the improvement is around 8 to 10%. And similar result can also be seen on the evaluation data in these rows. And and when we evaluate it on the mixed data, we also see a similar result to the mixed data. The overall performance compared to the DCASE baseline in this case is also around 10% absolute. One thing that I should mention that the DCASE challenge baseline is actually based on the heterogeneous losses, and we speculate that the same underfitting problem may happen with the DCASE baseline as well. And that may explain the poor performance of the DCASE baseline system. So to conclude, in this work we show that multitask loss function strongly influence the performance of job modeling for auto event detection and localization, and using the heterogeneous losses usually result in underfitting for the event detection task. And we also saw that it is much easier to train the multitask model with the homogeneous losses rather than the heterogeneous losses. Thank you for your attention.